Welcome to Musiquity. This is the DSCI 551 Fall 2020 project for Sriram. So let's get right into it. When I started Musiquity, the solvable I wanted to solve was first one, having a coordinated storage system that transcends data types. Mainly I was focusing on telemetric analysis so that I can take telemetry data in a time series format, use it with some structured data in MySQL and use that to store session data or certain stuff in a NoSQL database such as Redis or whatever, what have you. So in this use case, I'm using your hard data as telemetry on user information that's in MySQL, and that gives you NoSQL data that is music recommendations. So when I did this, another solvable I wanted to solve was platform or system agnosticism. That is, I wanted it to work no matter where you threw it in, whether it was a Raspberry Pi or a Windows machine or a massive server cluster. I just wanted to just run. So I'm using containers, which is literally a plug-up-play solution. Just run Docker Compose and everything comes up, and you're like done with minimal setup. Thirdly, I wanted to bring in Ubiquity and client-side abstraction. So no matter what my client side was, I wanted it to work well with my project. So if it was a web app, or if it was an Android application or an iOS application, it shouldn't really matter to me. So once I got that working, I could kind of scale this out so I could make it work on future platforms. You could probably, just make it work for whatever you build. So for this, I use web APIs, and these web APIs are really, really helpful because, HTTP is a standard protocol, and you can just dump in some data. Since you're not transferring a lot of binary data, it's just a lot simpler. So the data problems I tried to address here. First one was time series analysis and effectively storing time series data. So for this, I use retention policies. Typical retention policies are like 1 week or 1 month, after which all the data is just thrown out. So at that point, it makes sense for a user to use something like Spark or Hadoop or any distributed data storage processing pipeline, so as to aggregate all this data and say, for this user the average heart rate is this much, yada yada, what have you. The possibilities are endless. Secondly, indexing in terms of databases can be memory intensive, and especially in databases like InfluxDB, wherein a lot of your tags and your indices are stored in memory. The more indices you have, your cardinality increases almost exponentially, if I'm not wrong. This means that you need to store it in such a way that it's easy for the user to query. At the same time, it's also easy for your system to store it and not be overwhelmed. The next problem I had to face and address was data collection. Now, I used the Motion Artifact database as an initial jumping off point, and what I learned from there is that time series analysis of ECG data, or any data for that matter, is incredibly convoluted. On a regular day, it's really easy for you to kind of fix the problem at source by changing how you pull the data. But if you don't do that well and end up with time series analysis, such as what happened for me with this data set, you end up with a really complex problem that cannot be easily automated. It's a hard problem for automation, because you don't know what to automate, or you don't know the seasonality of your data, you don't know the trend of your data. So instead, I switched my primary source of data from a pre-built data set to a live data set, which is my own body. So I have my smartwatch, and my smartwatch uploads metrics to Google Fit, and I just pull that data. So data collection was where I had to kind of work with APIs and stuff, and as of now we do get metrics from the Google Fit API. And the next thing I want to solve was data storage and complexity. Now this is kind of a weird problem to solve, because you're like, wait a second, isn't this like a trivial problem? But it's not, because when you have time series data, when you have structured data, when you have unstructured data, you need to know that not everything can do everything well. No one's a jack of all trades. All of these are masters of one, and you need to make the masters of what they're masters at, and not let them worry about anything else. So I didn't want my time series data to worry about NoSQL paradigms. I didn't want my readers to worry about structured data and continuous and persistent storage. I didn't want MySQL to worry about JSON and time series. So at this point, I used 3 different databases, but I made them all interface with one another almost seamlessly. So when it comes to time series analysis, which was one of the major focus points of this project, the thing I had to worry about was auto-regression versus ARMA, artificial moving average, versus auto-regression with integrated moving average. So the solution for this is the fact that all of them work almost similarly, and auto-regression is like the easiest one to do. So that's where I chose auto-regression instead of any of the other two. It's more simple. It's maybe not as robust for really seasonal data like airline ticket prices or what have you, but it works for our use case, so I just went with that. Then user-generated metrics was what I explained in the last slide. I preferred using my own watch instead of getting ECG data from, I don't know, people who I probably have never met. In order to get that, I use Google Fit's REST API. Now, this is a bit hard to set up, but once you do set it up, it works really well with you. It aggregates sources from all your fitness apps, and it returns data to you. Having said that, this is the schematic diagram. This is how it all comes together. So, okay, I think my video is kind of blocking it a bit, but that's the Spotify Prep Recommender, which is used by the online ML system. Now, the online ML system requires, biometric data, which it asks the Django Web API. Now, Django Web API gets it from the data source, which uses Google's Fit, and so the Django Web API gets all that, the biometric data from data source, which is then sent to InfluxDB. So InfluxDB is then used by the ML system via the web API in order to generate predictions. Spotify Web Recommender returns recommendations to your ML system, and it sends it back to MySQL. Sorry, it sends it back to the web API, which then stores it in Redis. So you have your recommended system in Redis, and your UI uses UI based on React or whatever. It just pulls the web API, which returns data from Redis and what have you. So MySQL is mainly used for user metadata, like your tracks, what heart rate corresponds to what workout you're doing, and what have you. So that is usually learned or supplied by the user, and that's it. So you have Redis, NoSQL, InfluxDB, time series, and MySQL, which is a database, which is relational database working together in order to make all this come together. But when I did this, I did find a few challenges. So first part is that Fit API streaming is not really reliable. So sometimes it uploads in batches, at times it streams. So it's a future work, but I feel that if you build an app for your watch, you could be able to fix it. And persistent volumes in Docker are a little hard to bring out, but those can be handled too. It's a simple bash script. Then the truly distributed data storage systems, wherein you have each of them residing on a different machine. Now this is a trivial problem because all you have to do is fix the web API. And since we're using Google's OAuth, we have to handle recurring authentication and better token storage. So coming up next is probably our demo. Right, so this is the UI for Musiquity. This is our React application, the UI. So I am going to give in my username. I'm going to get data for this. As you can see, it generates the current heart rate, and it generates a graph of the kind of data is stored. So it's currently got like 8 data points right now. So it stored those. And these are the recommendations it gives me. So as you can see, there are a few of these songs like Never Forget and Rip and Tear. So this is, for example, a very peaceful song. And there are more of these. Like, for example, this is more. This is more, active. So it knows that I am currently in this phase wherein I'm not exactly relaxing. At the same time, I'm not in the midst of a workout. So it's able to recommend data to me. So as you can see, it's got some more data that says it's 85. Shouldn't be a lot of changes, but it does refresh your list almost every time you do it. Now this is the terminal. This is the server. As you can see, this is where I'm getting my data. And if you just do a docker ps-a, it shows you the dockers that are running. So I'm running MySQL on the local machine, whereas the other two databases are in Dockers, the Redis and the Influx. This is my front end. This is like my Polar, which gets from Google Fit API, throwing it into my web API. And this is my recommender system. As you can see, it's taking these seed tracks such as this and generating recommendations for my UI. Well, thank you for watching. The repository link is in the description. Please feel free to make a pull request, drop your comments, whatever you feel like. Thank you.